Yep. So we'll start the lecture with some repetition. So we had our drill string model. So the actual representation of it, a hole, this, well, walls, and we have our drill string as a pipe going down the earth, some kind of stuff that bores down here. Drill string. Yes. So that's the actual representation of one, or a model of it is a bunch of harmonic oscillators. Kind of string there. Mass element 0 down 1 to the last element 1 on and 2 and as the last element. So all of these mass elements, they have some kind of width, but no height. The height is in the springs. Spring height h, like so. Then you will also have this well casing on the outside, something like this. This height is small enough, then you see where you get the drill string, the different radius of the drill string. Okay, so that's our model. And then we did a lot of maths, which I'll try to repeat now. So to solve this system, we get a system of equations, which looks like m0, again the mass, q, that's the displacement. We need it twice time derived in time to get duration. Then we had gravitational force with some kind of buoyancy factor. So if it's buoyant, then less than just m times g. A spring constant q0 minus driving force big Q of time 1 q1 plus 0, and then we had some kind of viscous force, which we also did some math on. So in this case, those are the spring constants: K0, K1, K2, Kn, und so weiter. So this one is for the first oscillator, and the next one, I, Q, I, double dot, plus I, B, I, minus K, I, Q, I, minus Q, I, minus 1, plus K, I, 1, I plus 1 minus I, again this viscous force 0, and well, I guess, or 1 I minus 1. And for the last one, we are missing one of the strings. That is going to be M, N, Q, N, plus N, G, N, plus un minus un1 plus rn 0. Okay, so that's the first 10 minutes of the lecture. Next, we want to define this viscous friction force. Okay, so in order to do this, we needed the actual velocity component of a fluid particle, so how the fluid is moving inside or between the drill string and the casing itself. So we found an expression for, well, first the viscous resistivity force, which was, where is it again? Ri equals I alpha I. So alpha I, that was the ratio of the drill string, ratio of the radius of the drill string compared to the radius of the full borehole. So this is just a number between 0 and 1. Times r. This r is the radius. H, the length of the string. Mu, the viscous force. Then we need ui dr, actual velocity component. We'll evaluate this at the edge of the casing, and then forces from the mud pumping itself. E, depending on how much pump in. Okay. Next, we actually found an expression for this U as I R big U I R plus R over R squared plus some kind of constant D1 natural logarithm of R over big R. Okay, again, some constants we need to figure out were big U I is pressure gradient minus the density of the mud times gravity over 4 times the friction force. P1 constant we found to be Q dot plus U I squared minus alpha I squared over the logarithm of this fraction. Okay. Still need to find UI because we did this. Doing some clever math and looking at how we pumped mud through this system. Found QI be some kind of phi function of alpha I Q dot per R squared. Different placeholder for I, how much mud we pump through the pipe, P R4 squared, where phi of alpha I is, that was 1 over 1 plus alpha I squared. So I'm just going through this so we have the building blocks for later. This is a lot of stuff, so I assume overload. I of I over alpha I 4 plus 1 minus. So please arrest me if this is different from last time. Okay, then we had everything we needed to actually figure out this viscous friction force. I think. Sum up. Found out we can write it on the form minus zeta I pi by q I dot b I of b. Do you want me to also write the function for this zeta and b? Okay. So r I minus zeta I times q I dot. Is it different than yesterday? Just arrest me if it is. I've done something wrong. The I, where this zeta I 2 pi h u 1 plus alpha I squared over 1 minus alpha I squared logarithm 1 over alpha I minus 1 inverse of this, and the I equals 4 h mu b r squared, then complicated expression I squared logarithm alpha I divided by 1 plus alpha I squared I plus alpha I squared logarithm of alpha I plus a minus alpha I squared, then plus friction from the pumping forces. Like so. Then I think we have everything. Then we can start actually solving the system. And as you see, it's a kind of, well, it is a very complicated system. So in this lecture, we will try to make, or well, we will make this system of equations easy to solve by transforming our coordinates back and forth, and having fun with eigenvalues, eigenvalue decrease. There's going to be some heavy math, but I'll try to walk you through. Okay, so this system here can be written as big M as a matrix, displacement vector, or acceleration vector, I suppose, speed vector, and I'll define all of these matrices. Q G matrix vector V equals some kind of driving force. Vector, yes. Function of T. Okay, so this big M, that's all the masses. There's a diagonal matrix, M0, M1, weiter, N. That's basically just a diagonal matrix. You see that makes sense because looking at this equation, M is just in, so you don't mix the M's. You mix the. Okay, and this C, diagonal matrix of all of these data functions. 0, data 1, data N. That's these. Ri. Here we're splitting this R. R's. Have case, and we see that the string constants, they are mixed, because in the first one we have both 0 and 1. All the rest one we have both I and 1. K is going to be something like K0 plus 1 minus K1, K1, 1 plus K2, so here, there, minus 2, K2 plus K3, 3, oh, here, over here, lots of zeros. And you will get a banded matrix. Being K and 1 plus Kn minus Kn. And we're still up. So we have the G. Well, that's supposed to represent all of these rotational forces. We have G, M0, G, B0, M1, B1, B1, M, N. See, this is a vector, not a matrix anymore. And we have B. That's, again, just a vector of all of these B's here. And then I think almost everything. Vector is 0, 1, n as a vector. Okay, the Q's, again, that's the displacement from equilibrium for all of them. And now we're missing the driving force. And what's the driving force? Big Q, the driving force. So that's how you're drilling. How you apply the way to drawing, but it's how you apply force to actually drill. So you need to push it down. So you could either just push it constantly, or you could have like a sinusoidal pushing force going downward like this, or some kind of superposition of sinusoidals. They will give different responses for this drilling system, and you will explore different driving forces for this. Let me just last one. Okay, so this driving force F is a function of time. Okay, 0 Q of t 0 0 0. Driving force. Okay, so we can do something with this equation here. We can do some transformations, and if I say we can get it on the form, we can actually transform these Q's. We're going to transform the Q values such that we get rid of the G and V vectors. And a lot easier. So I'm going to introduce Q. So I will define Y later. K matrix inverse G plus V. Okay, so how do I invert this big K matrix? Is that possible? Do I want to do this? Should I do this? Well, yes. Also, it can be shown that this inverse of the K matrix equal to K1 hat, K1 hat, K1 hat, K1 hat, 1 hat. First one, and K1 hat. Here, K1 hat. Okay, do you think that's only K1 hat? So next one will be K2 hat, K2 hat, K hat. Down here, K2. Also over here, you will have K2. Then we'll begin with K3. Hat. So do you see the system here? So you have the well, like an L shape. One like this, and then you will have two this, then three like this, and then all the way down. In the end, k n minus 1 at k n minus 1 at k minus 1 at k n hat. And it's supposed to be a square matrix, for wondering. So that's the structure of it. But what are these K1 hats? Well, we are not going to prove it, but we can see that all of the K1 hats is a sum. J from 1 all the way I, K, J, inverse. So it's a fairly simple way of actually inverting this matrix. And doing numerical calculations, you could run into matrices like this. And then this relation is pretty nifty to have in order to be able to invert it easily. I mean, you could have attacked it with a well, different way of inverting it, but then you would need a lot more computational power to actually do it. Here you're just like, well, this is just ON operations, because you need to invert all of them and use sum. Fairly simple way of doing it. Okay, so what happens if I actually apply this transformation? And it's going to be a bit abstract, but okay. Applying this, I will end up with y plus b y f. And that's because if I try, so the way I've defined this, so these aren't functions of time. This dot vector simply y dot vector plus 0. And I mean, you need to also calculate this transformation, transform vector y, but basically putting that over there, equation. Fine. We should figure out the y. So you are kind of transforming how the displacement is a function of the spring constant. So you get some kind of weird or different space. But what we can see here, so we can have a sanity check on this. So if we don't have any driving force and the system starts still, so F, so just imagine that F is 0, there's no driving force, okay? And the system starts in rest. That is to say, speed is 0, and also the acceleration is 0. Well, then we say that we see that we don't get any change. Then this is 0. It's just a times y equals 0. We don't get any fluctuations. So we see that it makes sense. Sanity check for our calculations. So if you don't do anything with the system just stays there. That's what we want to do. I mean, you don't want to have a system that just like it's quiet, 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 and it suddenly explodes. That's a bad system. So it works. Okay, but we are going to do some more transformations. So I'm going to choose a new time scale also. We're also going to transform time. Yeah, that's good. So our new time scale is going to be 4, which is kind of CS, over the amount of dampers or springs times the regular time. So you're basically just scaling time linearly. Where DS is not Counter-Strike, but it's the speed of sound. It's and we will also write the spring constant properties. So E A over L there. E, oh, number 4, Young's modulus is A. That's the cross section of the spring. Area. And L, that's the length of the spring. Which we've previously called just H. Yep. Okay, and then we'll find some kind of geometric mean, all of the cross sections. Because the cross section could be changing, or most probably is changing along the drill string. We will take count of this. So I see did I already use an A? Yes, I'm going to use an A later. So I'm going to say that this cross section is a tilde over it. Because later I'm going to introduce some A matrices also. So to avoid confusion, I'm going to be preemptive. I'm going to call this AI. So that's a cross section at section I. Okay, and this tilde, that's just to set it apart from a parameter that or a matrix that crops up later. Next, I'm going to introduce the geometric mean of all of these cross sections. Is basically you multiply all of them. A, I, so, and nth root of this. Okay, so that's the geometric mean of all of the cross sections. Then we use more A's. This one we'll actually use, which is the normalized cross section. See the difference of all of these? Okay, so doing some fancy transformations and just redefining stuff, we can rewrite this again, or into the form using two matrices, and I'll introduce A1. No, this is a matrix because it doesn't have a tilde. My double dot ES for E. So that's the geometric mean of all the cross sections. The Y plus A2 Y equals H over Young's modulus A times driving force in time tau instead of time. At the time. What I'm actually trying to do now, I'm trying to uncoupling all of the equations such that it's easier to solve. Because in this, if you remember back, the K, that's coupled. I just removed it, but you saw it's a coupled matrix. Because it's not an how to say it? It's not a diagonal matrix. It couples each of the different oscillators. So I'm trying to uncouple them now, and that's why we're trying to use fancy maths. Before I can actually apply the fancy maths, I have to rewrite some of the matrices. So now I'm doing a transformation on M and K. E is still what it is. This new here, that's A1, diagonal matrix. Well, that's fine. That's the same as earlier. 1, 2, N, and to sure is a matrix. 1. A2, on the other hand, is still coupled. So we have, let's see this. 0, 1. Here, A0 plus A1 minus A1, 1. So you see this is fortunately still coupled. A3, 0, 0, diagonal, 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 0, minus A1, 1, plus AN, AN, N, AN, 0, and 0. And all of these are A's. I mean, the rest are A, not 2. There. Okay, so now we can start working on actually decoupling. Okay, so what do we know? About these? So we know that both A1 and A2 are so-called positive definite real matrices, meaning that for every vector, call it x. X p times a matrix. X is larger than 0 for all x vectors n times 1 except null vector. That's what it means to be positive definite. Kind of the definition of positive definiteness. And so due to this fact, we can use the generalized eigenvalue theorem, or we can solve the generalized eigenvalue problem, meaning that we have A1, this matrix X, lambda A2 X. So this is A1 diagonal 1 times or the generalized eigenvalue and different vectors. So with this, we can actually rewrite the equation such that we have this big lambda A1 big lambda equals the identity matrix. Oh, sorry. Post and post A2 lambda is some kind of diagonal matrix D. So next we're going to do linear algebra. We should decouple this system.